Another crucial aircraft system that you may think is limited to just the power plant semester, it actually fits very well into airframe because of how much of the system is integrated throughout the rest of the aircraft, and that's the fuel system. The fuel system there are a lot of different types, and there are a lot of different components that we have to learn about to be robust, highly effective aviation mechanics. That can work on anything that we come across because they're all very, very different. So in this class, we're gonna start talking through anything from the old like sight gauges on J3 Cubs with a aluminum fuel box to fuel bladders to capacitance using 737 fuel systems that you'll see in like the heavy commercial world. So buckle up.
All right, so we're going to start with the simplest of all the different fuel systems that are out there, and then build up in complexity. Now, this is an example of a type of system that you'll find in a high wing aircraft. So, say like a Citabria or a Cessna 172, or anything where the wing is mounted on top of the fuselage. Now, what makes these unique is that they're just gravity fed systems. So notice that there's no fuel pump involved at all. That you would put the fuel inside of the tanks there at the top. Those big white, oddly shaped tanks. I guess they're trying to make them look like big squares, but they didn't do a very good job. And then you'll vent those to the atmosphere. What that does is it creates a situation where the fuel always wants to go down because of gravity. They will then flow to a selector switch that typically you can put it on the left tank only, the right tank only, or both, which is an ability to it gives the pilot the ability to balance the fuel in either one of the tanks, which you're going to see be a reoccurring theme even with heavy commercial aircraft, is that you're always trying to keep the fuel burn uniform across all the different fuel tanks, so that way you don't get like a wing heavy situation going on. And then speaking of which, those tanks are actually in the fuel or in the wings themselves. They're up above everything. They will then come to a strainer, and that strainer is something that whenever we get to do an annuals, you'll have to pull that apart and clean it and everything else to make sure there's no trash in it. And then onto the carburetor, and then from the carburetor into the rest of the engine fuel system. Now, the primer is there as well. Usually, you'll be able to prime the engine from inside the cockpit with a little pump-like device, depending on the type of aircraft in question. But that is probably the simplest system that we're going to have. Okay, so for a high wing aircraft, you have gravity working for you, but if it's a low wing aircraft, say like a Piper Cherokee, or a Glass Air, one of the RVs, you're going to end up not having gravity work for you. The fuel is actually going to be kept lower than where the carburetor's at. So you have to have some way to get the fuel out of the tank and into the engine. And so the way that we accomplish that is with fuel pumps. Notice that I say pumps, plural, because there's always going to be two. You're going to have an engine-driven a fuel pump, and then an electric fuel pump that's commanded by a switch in the cockpit. You'll throughout the different stages of flight, you'll turn the electric fuel pump on or off. Like usually, it's on for starting. It's usually on for landing. Anytime you need redundancy that you wouldn't want fuel starvation to happen, you're going to turn that electric fuel pump on. You'll also, if you're operating at higher altitudes, there are certain situations where you're going to want to turn the fuel pump on to prevent vapor lock in the fuel tanks. And this is also going to be really important to remember to make sure that you monitor which tank the fuel is coming from. So typically you'll want to just keep it on both, so that way it goes evenly. But even then, you'll still monitor the two fuel gauges and make sure that, like, for whatever reason, one is overfeeding the other one. It could be the way that the fuel lines are routed, some sort of contaminant that you never know, and so you'll want to try to balance those fuel cells as much as you possibly can. But the main takeaway here is just notice that, like, it's not really that much more complicated. We just now have a pump involved, whereas with the high wing aircraft, it was just straight gravity feed into it. We don't need a pump because gravity's on our side. Okay, so this is a high wing with a fuel injection system. A little bit more complicated. You can see, like, as we kind of add layers of complication to the aircraft, the fuel system gets equally complicated as we go. All right, so a couple of things to take away from this one is one is that there's a fuel control. The fuel control unit meters the fuel according to engine RPM and mixture control inputs from the flight deck. So meaning that as the engine RPM changes and as the power settings from the pilots change, there's going to be a different appetite for fuel to the engine. Well, under a gravity fed system, the gravity just simply pushes the fuel down to the carburetor, and the engine takes what it takes. And under a fuel pump system, the fuel is just delivered to the carburetor, and the engine takes what it takes. Now, on this situation, you're a lot more in command of how much fuel actually goes into that engine since it's fuel injected. So the control unit is the unit that actually will control that. It will dictate how much fuel actually goes. So that's an addition to it. Additionally, the fuel control delivers the fuel to the distribution manifold, which divides the fuel up and then provides equal, consistent flow to each individual cylinder. This is what it looks like. It looks almost kind of like this like spidery looking thing that sits on top of the engine. The you can see the main fuel input comes in on the left hand side there at that little 90T, that little AN fitting, and then it hits the manifold and then gets distributed out to all the different cylinders. And then you have a return on the other side for any fuel that doesn't get used. It goes back into the fuel pump and then gets pumped back into the tanks. Now, under this system, there's also something that's unique about the fuel tanks. It's not just the fuel tanks like we've previously seen. They also have reservoir tanks that will be gravity fed from the main fuel tanks, and then it comes in there. Now, these have like a very low amount of airspace, and allows for that fuel to more or less to be primed, but that's not necessarily the right terminology for it because priming is its own thing. But essentially, but to make sure the fuel is always there, because what you don't want to have happen is air to get into this system. That will cause issues and stuff. It'll work itself out to a certain degree, but like you definitely don't want to you want to avoid air at all cost. And so having those reservoir tanks right there helps with that, having that fuel on demand right there whenever it's needed. So that's high wing with fuel injection. Okay, so this is a low wing twin engine fuel system. Now, this graphic is a little bit busy because they've included a couple of other things that weren't on the other ones. So, for instance, like the indicating systems that are on there, we haven't really talked about. They are also present on all the other systems that you've seen. They just weren't on the graphic for whatever reason. But to kind of knock those out, you have a fuel quantity indicator. Obviously, you're gonna need to know how much fuel is in those tanks. It's also a kind of like one of the bare minimum requirements. So like the good acronym to know like what's the bare minimum requirements for a VFR aircraft in terms of equipment is A tomato flames. One of those letters in A tomato flames is you have to have a fuel indicating systems. You have to know how much gas that you have. You have one for the primary cells, and then you have an auxiliary fuel tank quantity indicator as well. The only other dial is the dual fuel flow gauge, so you need to know how much fuel is actually flowing to these two different engines. That takes care of that, immediately. Now the notice that there's two selector valves. That for both sides of this aircraft, so you could configure it to help try to balance fuel. Now you can't cross feed these under this system, but what you can do is basically turn one side off, turn the other side on, and make it like flow across to the other engines. Now Other things to take out is that the vapor separator is also there about midway down on the graphic. What the vapor separator does is basically just helps remove air from the fuel, which you don't want. That's going to cause hiccups in the firing cycle of the engine, and that's never a good thing at all. Other than that, everything else is um, fairly straightforward. We've seen those on the other graphics as well. Minus they have the left oil dilution solenoid and right oil dilution solenoids. Don't pay attention to those right now. We don't want to get into that. But other than that, just notice that like anytime that you're adding, the kind of big takeaway for this graphic is that one, there's a vapor separator on it, and then anytime that you add two engines to it, everything starts becoming a lot more complicated. Not just because there's two of everything, but also because they're all interconnected to each other. So that makes troubleshooting a little bit more difficult. It also makes just simply like the amount of parts and pieces and the routing of all the different lines and all the good stuff becomes a little bit more difficult. Okay, so like large heavy commercial aircraft, your transport category aircraft are going to largely look the same. So we're just going to talk through the 737's fuel system, primarily on the right side. All right, so the fuel tanks are integral, just like they're built into the wings and into the fuselage of the aircraft, and they all have boost pumps that grab the fuel and they pump it up and out to the engines. Now there's a series of valves that allow for cross feeding, so like that you can balance that fuel weight out across all of the different fuel cells in flight. And eventually you're going to get to a spar valve that basically is kind of like the main turn on, turn off, like fuel valve for that engine. And that's once that spar valve is opened, fuel is going directly to the engine, and the engine takes it from there. But that is, it is as big and as complicated as a 737 or any other heavy commercial aircraft may be. That's how straightforward the fuel feed system actually is. Now, there's a bunch of other systems that make it a little bit more complicated. So if you look at it, you see like fuel lines going all over the place, and valves and pumps. But for the fuel feed system, it's pretty simple. It's really boils down to you'll have a fuel cell with a pump that will go to a valve that goes to the engine. Not unlike some of the other low wing systems that we've seen so far. So don't ever be intimidated by them. They're actually pretty straightforward.
Now we understand a little bit about the fuel system types that are out there and the different types of things that we could potentially come across. Let's talk about some of the characteristics of the fuel that we're going to be putting in those systems and how that impacts the fuel system as a whole.
All right, so there are a lot of different types of aircraft fuel that you could potentially come across in your career. One of them that I've worked with in the past that's not even on this chart was JP8, which is the primary fuel for most of the military. So most of the aircraft get that as well. However, there's two beyond the rest of these that you're going to see pretty frequently. That's 100 low lead avgas and then Jet A. Now, we're going to talk about 100 low lead first, and that's when you hear 100 low lead, you're going to think general aviation. So like your Piper Cherokees, your Cessna 172s, all the small aircraft. That's basically what you're going to think, all the way up until once you start getting into turbine aircraft. So, like say, like your King Airs, your Pilatuses, TBMs, anything that has a turboprop on it. That's whenever you start seeing Jet A come onto the scene. Now, I've never seen 82 UL avgas. I've never even heard of that before. So that's probably not something you're going to come across. 100 avgas I've heard of, but I've never actually seen, because 100 low lead basically is the standard across, at least across the U.S. And it's difficult to get in third world countries, while a lot of like these like Bush carriers, mission aviation operators They went away from using like the Cessna 206, the 182, the 185, all that good stuff, and then started using like the Caravans, the Quest Kodiaks exclusively because Jet A is actually pretty easy to get. It takes a lot less refinement, it's a lot more available because the transport category aircraft all use it. Whereas 100 low lead is only used by small general aviation operators, and small general aviation operators are actually in short supply around the world outside of the U.S. And so 100 low lead is actually kind of difficult to get. So Jet A, however, you'll see that all over the place. So those are the two that we're going to kind of fixate on and talk about. Just know that there's other types that are out there that are going to be similar to either 100 low lead or Jet A, but you probably you shouldn't encounter them, especially in this day and age. Okay, probably one of the most distinguishing features of avgas is that it's blue in color. So that's like I said, it's going to go with small reciprocating engines, and whatever fuel you end up putting on an aircraft should be clearly denoted on the fuel port itself. It'll say 100 low lead only, or Jet A only, or whatever. Anyways, so what this person is doing right now is they're sumping the tanks on what looks like a 182 or a 206, something like that, and you'll notice that it's poured into that glass and it's that blue in color. Now that blue dye that they put in 100 low lead makes it easy to identify. It also helps you find fuel leaks in the system because if you expect a fuel leak there somewhere, it's almost always going to be this big blue spot because what happens is the fuel leaks out, it evaporates, and then it leaves the dye behind, leaving a big blue mark either on the hangar floor or on the wing or wherever. And a couple other things like to kind of remember with avgas is that it's really volatile. It means that it evaporates very quickly. It's very unstable. Makes firing really good inside the cylinder, but it also means that it can very easily catch on fire. Whereas Jet A is more like kind of like diesels, like the kind of you put a cigarette out in it and all other good stuff that people will say about diesel fuel. But like avgas, on the other hand, will 100% catch on fire at the easiest, at the slightest spark or presence of a flame. So that's something you always want to be aware of. And remember that the fumes that it puts off is heavier than air, and so they're going to pile up in any kind of low spot. And so, like, you might be doing some kind of like big fuel operation in one place, but if the fumes hit and they go downhill and they don't have enough time to dissipate, they can pile up, and then somebody go down to the smoke pit, light up, and boom, like you get a big explosion. So these are just things to keep in mind with avgas. Now, because of that volatility, any system that uses avgas is going to be subject to potential vapor lock. Vapor lock is where the fuel effectively evaporates in the line and then more or less just locks up the entire system. So there's a lot of steps that can be taken to prevent vapor lock, like the use of boost pumps located in the fuel tanks that force pressure liquid fuel into the engine is probably the most common. Matter of fact, it's like almost ubiquitous. Like you're going to see it all over the place. Okay, so another kind of danger with avgas because you're using downdraft carburetors a lot of times is carb ice. We won't go into a whole lot of like how this happens or what it is. Essentially, like you just have water vapor that could potentially be in the fuel that whenever it gets squeezed through the carburetor, the temperature drops, and you'll start to see ice start to form on the carburetor. There's almost all aircraft are equipped with carb heat, and we'll don't want to go too far into the details, but essentially it heats up the carburetor, melts the ice, and then the water vapor just passes the engine unharmed. Not a huge deal, but something you have to be conscious of as a pilot, and then also as a mechanic. If somebody comes and starts complaining about, hey, look, the aircraft was doing this, you'll know that, hey, carb ice is a thing, and maybe that's what they had, and that's what caused the problem. Okay, so pre-ignition or surface ignition is another thing to worry about with reciprocating engines that avgas is kind of subject to. Is that effectively what happens is that you get a hot spot on the top of a piston, and whenever either caused by some sort of trash left over or not fully combusted fuel or any number of things could lead to it. And then whenever the fuel gets injected it into the cylinder during the compression phase of the engine, it explodes before it's actually supposed to, and so you're like flying along, everything is happy hunky dory, and all of a sudden the engine starts just like really like being violent, and that's could potentially be because of pre-ignition. Okay, so another concern with avgas is detonation. That's the rapid, uncontrolled explosion of the fuel due to the high pressure and temperature in the combustion chamber. The fuel air charge ignites and explodes before the ignition system spark actually lights it off and it's supposed to burn. And occasionally, detonation occurs when the fuel is ignited via the spark plug, but it explodes before it's finished burning. And so this is why we have lead in 100 low lead. It's actually supposed to prevent this thing from happening. However, it can still happen if you don't operate their engine correctly or do a couple other things. We'll get more into this in the power plant and talk a lot more in detail about how to prevent it and how to detect it whenever it has happened, because that's another thing that you'll have some dude show up at your shop and be like, oh, the engine did this thing or whatever, and you're there having to try to figure out what it is. Well, you'll pull out the cylinder and it'll look like this, and you'll know, oh, it just detonated on itself. Okay, so issues with jet fuel are actually a lot more benign, but also harder to detect. So the first one is that like jet fuel will freeze. It has trace amounts of moisture in it, and it'll set up and freeze, and that whole engine will become a big block of ice. It's like a major deal the further up you go in the northern latitudes, to the point where they'll end up putting like heating blankets on engines because you also have problems with the oil doing this. But one of the main things with the fuel is that they will put additives in there, like Prist being the main one that everybody uses to help the fuel be prevented from freezing. Now, when we get to power plant, we'll talk about like fuel heaters and things like that are engine driven to actually help melt some of this fuel to keep it from becoming a big block of ice. But know that is one of the issues with turbine fuel, is just simply it just freezing in cold weather. Okay, another thing that will happen with jet fuel is microbes will actually eat it. So believe it or not, there's actual microbial life that will live off of hydrocarbons, i.e. jet fuel, and they'll consume it and leave their waste products behind. So you can see how pretty quickly this is probably not a good thing for any jet engine or any turbine engine fuel system. So we have different biocides that actually get added to the fuel that helps kill that off. Now, generally speaking, most of the time, those aircraft will turn over fast enough to where this isn't an issue. However, if you have an aircraft that is sitting up a lot, that's turbine engine aircraft, this is something you might end up having to look into. You'll be able to start picking up that you've got a problem with your fuel filters because like all that trash will end up getting it'll get it getting picked up by the fuel filter, and you'll know that, hey, look, I need a biocide additive to my fuel. Not a big deal to add it. You just follow the directions and add that additive to it, and yeah. So that's really the only two big issues with turbine fuel is that freezing and microbial life.
Okay, now that we understand the system and the fuel types, let's talk about the individual components of the different fuel systems that are out there. There are some that are very, very unique to just that in particular type of fuel system, say like a bladder, and there's some that are almost ubiquitous, like they're going to be all over the place, like fuel pumps. But what type of fuel pump? There's all different kinds of fuel pumps that are out there. So let's talk about that.
Okay, so the first kind of component that we need to talk about is just fuel lines. Fuel lines we've already talked about at length in general. We actually built some of them, so we're not going to go over them too much more. Just know that this is a typical flexible aircraft fuel line with braided reinforcement. You notice you have the synthetic tube that actually touches the fuel itself, the fiber braid that goes on top of it. Then there's usually a synthetic cover that goes over the top of that, and that fiber braid really just helps reinforce it keeps it from from getting cracked or damaged, and then you'll be able to see the damage usually on the synthetic cover on the outside. Once you start seeing that damage come in, it's time to build a new line and replace it. Pretty straightforward. Okay, so one thing that's common across all fuel systems are fuel valves. Now, fuel valves, even though they're common, they're all going to look different and they're going to be used for different things. This one is a common general aviation fuel valve that's a selector inside of the cockpit itself. Notice that you have a big red indicator of where which tank the fuel system is drawing from at that in particular point in time, and then you just grab it and move it over there with your hand. You'll basically, as you're flying along, you'll turn on the fuel pump, make sure that you maintain fuel pressure, and then as quickly as you can go from one little detent to where that fuel is sitting right now to whichever tank you want to go to, and you'll make sure that it sits in the detent. You'll feel it click into place whenever that fuel valve is set. All right, this is a cutaway of what one of those valves will potentially look like. Notice there's the detent plate that's underneath there, and it's spring loaded to help push that detent plate up whenever it gets into the right position. And it's pretty straightforward, pretty simple. You'll have a fuel line that comes in. You spin it so that way the opening of the board passageway, as they call it in this, the opening in there aligns with the outlet port and all. Okay, so heavy commercial aircraft are going to have a bunch of valves. However, they're not going to be the hand-operated poppet type valves that we just talked about. Instead, they're going to be little electric motors that open the valve and close the valve, and then they'll give an indication to the cockpit of whether or not they are either A, open, B, closed, or C, in transition. And so in transition means that they're in the process of opening or closing. And you're going to end up having to deal with a lot of these valves because they tend to go out for whatever reason, or get stuck, or not do the thing that they're supposed to be doing. Now, they have a little red indicator on them. And that will allow you to be able to go down there and manually see where that valve is at. Is it open or is it closed? And you can also grab that little red indicator and drive the valve. You can actually open it or close it with your hand to see what's going on. Now, this is really important to remember because a lot of times they'll say like, "Hey, look, this valve is stuck in such and such a position." Well, you can go up there and grab that valve and then pull it to the position you want it and let go. Now, if it immediately returns and you'll hear the little electric motor drive and go back, you know that the aircraft is commanding that valve to go there, and the valve is probably working just fine. It's getting the wrong signal somewhere, so you have an electrical issue somewhere further up the chain towards the cockpit. Now, if it goes and stays there, then you tell it to go back into the other position, and it doesn't want to do it, then the valve is fried. So it's a quick and easy troubleshooting tip to go through with all these fuel valves. But they're really easy to install. They're really easy to troubleshoot. And they're really easy to operate. They're just really simple DC motors with this little lever on the outside that allows you to open it one way or the other and kind of go from there. Okay, another type of a valve that you can come across is a solenoid operated valve. You can see how this one's pretty simple. You close a circuit that causes that solenoid to operate a certain way to either close or open that valve via that little tapered stopper that's there. And that allows the fuel to flow or or to either flow or stop flowing based on whichever position you want it in. Now, to be honest with you, I've never actually seen one of these on the fuel system anywhere. Most of the time, it's either one of the poppet type valves or the detent type valves that you see in the cockpit of small GA airplanes, or you'll have the motorized type valves that you have on large transport aircraft. However, these are definitely out there, and you'll probably run across them at some point or another. Okay, so another very common item that you'll find in fuel systems are pumps. Now, the pump that you're looking at here is a wobble type fuel pump that is literally like used by actuating that handle, usually in the cockpit, and it'll pump fuel to where it needs to go. Typically, this would be like a primer on an older aircraft that you don't generally don't see that much anymore, unless you're working on like antique aircraft that are out there. But the main takeaway is that like every fuel system that's out there will have some sort of pump system tied to it somewhere in the mix. Even though the old, like high wing downdraft carburetors like your J3 and stuff, they still have primers on them, which all the primer is a type of pump. All right, so speaking of primers, this is what they look like. You have an inlet and an outlet on there, and it'll be hard mounted typically to the dash of the aircraft. You'll unseat that primer and then pull out a plunger arm, and then you'll push it back in. And what that's doing is that's pulling fuel out of the fuel tanks and then pushing it up into where the carburetor's at, which allows the engine to fire off and then get the fuel pump going, so that way it can feed itself. But that is the whole purpose of the primer. It's basically just a little simple pump that's on the dash of your aircraft. Okay, a centrifugal type boost pump. Boost pumps are used all throughout aircraft fuel systems. The first time I ever encountered was in the fuel system of a OH-58. We had one that was at the center of the tank at the very, very bottom, and it was mounted kind of like the one you see here on B, but it was upside down, so that way the motor actually kind of stuck out. And you would turn that on, and what that does is it swirls the fuel on the inside of the fuel tank, and then there's a line where the engine's going to dry or going to pull fuel from, and it was pushing fuel into that, so it's pushing it up, and then there's other pumps along the way to grab it and pull it the rest of the way and deliver it to the engine. Very, very common in pretty much all aircraft fuel systems is a boost pump. Okay, this is a cutaway of what one looks like. Notice that you have an impeller down there at the bottom, kind of like an impeller on a outboard motor. Spins around, grabs the fuel from where it comes in there on the inlet screen, and this one's going to pull it up and pressurize it as it goes up through a check valve and wherever it's going to go. Now these boost pumps, you'll end up having them at different stages in the fuel flow process, and anywhere that it starts to slow down, generally there's going to be a boost pump there that's going to turn the impeller on. It's going to suck on one side and then push out on the other side where there's a check valve, allowing that whatever pressure leaves the check valve will stay in that line, because there's no chance for it to come back and actually lower the pressure at all. Now, those boost pumps have to maintain what they call their prime. They have to have fuel that's delivered to them on a regular basis, because if not, whenever you turn the boost pump on, if there's just air, what will happen is that it'll start to spin. It will get really, really, really hot, and it's going to lock up, or it's going to have the impeller come apart on you. So, in order to combat that little issue, ejector pumps were installed. Now, all an ejector pump does is it uses a venturi to pull the fuel up to where the boost pump's at, and that allows for that fuel to always be right there where the boost pump needs it to be, so it never loses its prime, and you have to worry about it failing. Okay, another type of pump that you could see, especially on small general aviation aircraft, are pulsating pumps. Now, these work kind of like a pump jack in an oil fill. You'll have a magnet and a solenoid coil that causes a little plate to move up and down. Now, as that plate moves up and down, it pulls fuel in and unseats the little ball valve at the very bottom, and then whenever it pushes it back down, that pressure has to go somewhere, so the fuel goes out. And this happens really, really, really fast. But you'll see these types of fuel pumps on GA aircraft, small GA aircraft, usually mounted on the firewall. Okay, lastly, we have the vane type fuel pumps. These are your engine driven fuel pumps you'll see on like little, Lycoming engines in general aviation. Now, these work basically like every other pump, is that you have a vane that pull goes one way, leaving a gap which that creates a suction which grabs the fuel and moves it into the pump, and then it's going to turn around and push that fuel through a small outlet on the other side, and as it pushes it through that small outlet, it's going to squeeze it. It's going to put it under a much higher pressure. It's going to push the fuel down the line, and then it's going to continually push the fuel as it puts more and more fuel into the line. Now, these types of valves usually have a pressure relief valve that you can adjust the fuel pressure with as well. What that looks like is that you'll have a pressure adjustment knob on top that will screw in, and it basically screws that valve seat either open or closed. If there's an overpressure situation, what will happen is that the fuel will go around that valve seat and then enter the pump. Basically, you've kind of created a big space for that fuel to go into, which helps lower the pressure of it. If you want to increase the pressure of the pump, then you would screw that adjustment all the way in, seating that valve, and then basically not allowing any fuel pressure to bypass it and then get around and have to circle back around. That will raise the fuel pressure, or you can lower it by simply doing the opposite, by unscrewing it and bringing it back up. But if it overpressurizes, it'll collapse the spring and then keep the pump from getting blown up with too much pressure. Okay, so filters are another integral part of the fuel system. You're going to end up hearing them described as like a 400 micron filter, or a 10 micron filter, or a 1 micron filter. So I'm going to give you an idea of like how big a micron actually is. So this graphic here shows the human hairs, whatever they is sitting on. Your hair is 100 microns. So that just kind of put that into perspective. A grain of salt is about 60 microns, and you start getting into the really absurd size, like a neuron cell's 4 microns, and bread molds 2 microns, and anthrax is a 1 micron entity. And so whenever they talk about a 10 micron filter, they're talking about filtering out things that are the size of about 10 anthrax cells. So a micron is absurdly small. So just keep that in mind as we talk about these filters. Okay, so many light aircraft use these. They're fuel strainers. All they do is basically pick up any large particles that might be floating around in the fuel and not let them pass. That effectively what will happen is the fuel will enter into the strainer, and it kind of goes to a basket-like mesh that catches anything that's really, really big. However, it won't catch small things. Usually small things are the things that really mess up the fuel system. But if it's got some kind of large trash floating around in it, these will definitely pick it up, grab it, and hold on to it. You'll often see a drop in fuel pressure, because they then will effectively turn immediately into a clog, and when that fuel pressure drops off, you're not going to get the same performance you are. So if it does catch anything, you're going to want to almost immediately see about trying to figure out what that thing is and then start fixing it. Another fairly small and antiquated filter system is a gascolator. You'll see these on older aircraft. They will often be clear glass there, but they don't necessarily have to be. They can be metal. What happens is the fuel enters into the bowl there, and then goes through a strainer, and then hopefully leaving behind any contaminants there at the bottom of the bowl. So, like a lot of times when you're pre-flighting, you'll want to sump the tanks, get any contaminants or any water out, but you'll also want to sump the gascolator and get all of that out. Now, during annual, you're gonna unscrew that knob and take the whole thing apart, clean it out, make sure that there's no contaminants floating around in there, and then put it all back together again. Now, most filters that you end up working on have filter elements that they get replaced. Now, the strainers and the gascolators, that they don't. You just clean them out and put them back together, and that's it. But they don't really filter. They just kind of strain the fuel, make sure there's no big trash floating around in it. An actual filter itself will have a filter element that you can take apart and then replace every so often, or whatever the the maintenance manual calls for. Now, this is an example of one. It works just like the gascolator does. Essentially, you'll have fuel that will come in over the top of the filter, and then on the interior of that filter, it'll start to pull a suction, and that will pull the fuel through the filter and capture anything that's there. And you can have up to a 10 micron filter. Just know that like the more it filters, the slower the fuel flow is going to be. So you might require another pump later on or whatever. Now, some other filters could have a what's called a double screen construction, where you have one screen that on the inlet side, as the fuel enters it into the filter, gets screened once, and then there's a more fine screen on the inside so as that fuel gets filtered once as it comes into the filter housing, it'll go to the bottom and then get sucked up into the outlet, and whenever it does that, it has to pass through a very very fine screen right there. So like these filters right here will basically collect anything and everything. It's most common in your heavy commercial aircraft or your turbine aircraft specifically. Anything that from a turboprop up, you're going to end up having to have really robust fuel screening, because the error for fuel contamination on those engines is very very slight. Okay, here's an example of kind of a generic turbine engine filter that uses a cellulose element. So you notice on the left side, the fluid or the fuel comes in, passes through a baffle, and then into the actual filter element itself. Now this is a 10 micron filter, so it's going to have like the highest degree of filtration for any fuel that you're going to end up having. You'll notice that it passes through the filter elements and then into like another interior screen. Now, typically the way these will work is that like the cellulose part you'll throw away and replace every so often, and the screen you'll rinse out. Like you'll take fuel, then you'll pressurize them, or you'll put it into a parts wash tank, or whatever your whatever your situation is, and get it all nice and clean. You'll reinstall the permanent filter, and then you'll replace the filter element itself. Typically, they're kind of conical in shape, and or not conical, but like they're cylinder in shape, and they nest inside of each other. Then you'll put the filter bowl, put them inside the filter bowl, put the filter bowl back on the housing, and then you notice on this graphic it has like a little a nut on top. Those are very common, and you'll screw those down. Now, typically, the relief valve is not offset like that. It's usually integrated into the housing somewhere else, and you generally speaking don't really mess with it unless the filter gets clogged and it pops the housing. Anyways, once the fuel passes through all that, it goes in the outlet and off you go. Now there is a drain valve there for maintenance purposes, but typically you don't ever mess with it unless you have to for one reason or another to get it off. Now what's important about these is that they're the first line in engine defense for any kind of fuel contamination. What will end up happening is that if you have, like say, like a pump failure or a valve failure or some sort of contamination, the first thing that's going to happen is you're probably going to end up clogging up a filter, and you're going to get a pressure relief valve or a pressure bypass indication. Because anytime those little relief valves pop, generally speaking, they will send an indication to the cockpit that says like, "Hey, look, you're in a fuel filter bypass, situation," and that lets you know that there's something that's clogged in the fuel filter just all of a sudden like that. And so what you're going to do is you're going to pull that filter apart, look at it, and say like, "Hey, look, what's what's in the filter, what's clogging it up," and then you're going to start to kind of like backwards engineer what the problem was until you eventually figure out what the primary issue is. All right, so this is another variation of a turbine engine filter system. It's called the wafer type. That wafer screen that you see right there in the middle gets replaced, and then you have a filter disc and a core that basically stays permanent. Depending on the aircraft, the engine, all that good stuff, things could change, but that's generally how it will typically go. You'll replace the wafer screen every so often. The difference between this one and the last one was made out of cellulose, so it's like a paper filter. This one is a kind of like almost like a metal-like device. You also will take that filter disc and the core, and you'll wash them out in your parts bin or your parts washer or into a thing of fuel or whatever, and then you'll reinstall them with a new wafer screen type filter. But yeah, so that's it for fuel filters.
All right, now let's talk about the aircraft fuel tanks and cells and the different configurations that we could come across and the maintenance practices that go along with them.
Okay, so there's three basic types of fuel cell systems that you're going to come across. One is the rigid removable tanks. The next one are the bladder tanks, and the last one are the integrated tanks. Now, a rigid removable tank is exactly what it sounds like. It's rigid. It's usually like a big, typically aluminum box that you can take in or out of the aircraft as needed for maintenance. Now, there are other types that are out there. I've seen them on beavers that are they're like kind of like plastic, translucent, really thick type of like plastic, like you'd see like livestock watering boxes and things like that. But aluminum is probably by far the most common. Now, what you're seeing here is a graphic of kind of one of those rigid removable tanks. Now, you have your typical vents, a scupper and a filler cap, and all that kind of stuff. But what I want to point to you is the baffle plates. That's what I really want you to kind of hone in on. Now, it's not that they're unique to rigid removable tanks or anything else like that. They're unique to fuel tanks in general. And those baffle plates are there to keep the fuel from going way too far on one side way too fast and causing a unsafe flight characteristic in the plane. You put the baffle plates up and you offset them so that way as the fuel like moves whenever the plane banks, the baffle plates basically slow it down and allow the fuel to just ease over there nice and easy, rather than like sloshing one way or the other with this massive change of weight and momentum inside of the wing or inside of the fuselage tank wherever it's out. Now, that's going to be common through just about all of the fuel cells except for bladders. Now, other than that, there's not a lot to really be said about a rigid removable tank, other than it's a box that basically goes in and comes out and is a fuel cell, just like any other fuel cell that you're going to encounter out there. Okay, so the next one we're going to look at is bladders. Now, bladders are common kind of across aviation. I've never seen them on a transport category aircraft, like a heavy commercial aircraft, like a 777 or something else like that. They don't have those there. But in general aviation, there's all kinds of aircraft that actually use them. Cessna 210s, some Cessna 182s. The so at least the OH-58 had a bladder system, and it was a pain to get it in and out. I'll tell you that. Now, granted, the OH-58 is a little bit different because the fuel system is bulletproof, so that way if you shot the tank, it would self-seal and not just like leak fuel all over the place. These bladders aren't necessarily that way, but they, I guess, potentially could be, depending on the aircraft and the model number of the bladder itself. The idea with the bladders is that you were able to compress them down, slide them into the wing, and then inflate them so that way they would take up the full expanse of the wing in there, but have a rubberized seal so that way the fuel could never leak out. Now, I'll tell you that is a good idea in theory, but in practice, these things will also leak. And then what's more is that they have a kind of an end date on them. Like, you have to take them out every so often, and it is a task to get these things in and out of the wings where they're stored. Integral tanks and rigid tanks are the way to go. The bladders are kind of a thing. They're a thing. I won't say a thing in the past. They're still out there, but they definitely are not being put on any new airplanes. Like, I think a lot of people have realized the error of their ways when it comes to installing bladders on aircraft. But this is how they work. Essentially, like they're just like a rigid, removable tank, except for they're just made out of rubber and then they are flexible. It's pretty straightforward, pretty simple. All right, so the most common type of fuel cell that you're going to run into out there is the integral fuel cell. It's a fuel cell that's built into the wings and body of an aircraft. Now, this is common on even on my Piper Cherokee all the way up to 737s. So if you look at the fuel cells of the 737, you'll notice that there's surge tanks on the tips. You have a main one, main two tank that basically takes up the vast majority of the wing, and then you have a center tank that sits in the main fuselage. Now, you can feed both engines off of any one of those tanks by itself. You can cross feed them. You can link them all together. One of the kind of like interesting, I guess, tidbits about the way that the fuel will flow through these tanks is that if you remember back to TWA Flight 800 back in the early 90s, so they thought it was shot down by a man pad out in the middle of the ocean. Actually, what ended up happening was they had drained their center tank first, which was kind of a common practice at the time. Because if you think about it, like let's get the weight off the center of the aircraft before we start playing the balancing act of making sure that we burn main one and main two simultaneously. And this was a 747, it has a lot more fuel tanks that are out there. Anyways, they did that, and what ended up happening is they left a lot of fuel vapors in that center tank, and then there was a arc because of a HF radio antenna that passed through there, and it caused it to explode. So it's people that saw the explosion. They literally saw 747's fuel tank explode, and so they thought that it was a missile that hit him, and so it led to a lot of drama back in I think it was 91, 92 about this. But anyways, all that being said, now these integral fuel tanks, the rule is that you have to drain from the center tank. So those tanks will feed out of the wings and into the center tank and out to the engines to prevent one factor of that from happening at least. Now that being said, that this is just an example. Like this is a 737 Max, fuel cell placement. You could have more fuel cells out there, and they could also be, you could have them up and down the fuselage, multiple tanks inside the wings. It just really depends on what the mission of that aircraft is, and how it's built. But yes, but the takeaway with integral fuel tanks is that they're just built into the aircraft, and so they look just like a rigid removable tank, except for it's part of the aircraft structure itself. Now, that 737 has access points, so that way you can get up there and work on the fuel cells. And this is something that you'll see done on multiple checks, troubleshooting issues, you name it. You'll have a bunch of rules about accessing these fuel cells, because some of these are big enough where you can get people up literally inside of them and be moving around and having to replace boost pumps and fuel senders and all kinds of stuff. But these access points, there are up and down the wing. They're a little circular, so next time you fly, just look out the window of the aircraft and look at the wing. You'll see these little circular access points there on the top and the bottom, and you should be able to just pull those guys off, and then be able to get up into the fuel cell and do whatever maintenance needs to be done, and then you reattach them, and off you go. There are two places for boost pumps to be installed, and keep in mind the wing slopes downward towards the root, and so all that fuel should eventually end up where those boost pump access panels are at. And the reason being is that you always want the boost pump in the sump because it has to remain primed. So that is the 737's integral wing tank. Now, integral wing tanks, like I said, like will be different on every single aircraft. This is just the 737, but they all will follow kind of the same construct. Smaller, older airplanes may not have as many access panels or any access panels at all, like for instance the Piper Cherokee. But most of your heavy commercial aircraft are going to have maintenance required on them, so this is how you would access them, and they'll have plenty of access panels for you.
All right, now let's talk about the Fuel Quantity Indication System, FQIS. They are as varied as any other type of system on the aircraft. You could have capacitance systems to sight gauge systems to float systems to you name it. So let's talk about all those and get a good solid understanding of what we need to do as mechanics concerning them.
Now, Part 91 demands that every aircraft have a way to tell how much fuel is left in it. And the reasons are obvious. Like, one of the primary causes of forced landings is fuel exhaustion. People just don't know how much fuel they have, even with the gauges and the rules. But that being said, every single aircraft is going to have some way to tell what the status of the fuel is on board. And they can be very, very simple, and they can be very, very complex. So what you're looking at here is the fuel gauge on a Piper Cub. Notice that it's literally a float with a rod on it, and as the fuel goes up or down, it moves the rod up or down. And so that way, whenever the fuel is nearly exhausted, the rod is really, really short. When the fuel is totally full, the rod is pushed all the way to the top. Now, this is the original design. There's been several modifications come on that's changed this, but this is the way that you would be able to tell the level of fuel that's inside of a Piper Cub as you're flying it. Here's another mod that came about with the Cubs. Essentially, like since you have a point where the fuel can flow into from the bottom and all the way up to where it's going to be full and flow back into the fuel tank, and water seeks its own level, or liquid seek with their own levels, you can literally just look up and see where your fuel is at on one of the wings, and it'll basically tell you, hey, look, like you're all the way up, full or three quarters or so on and so forth, all the way down, and then you know how many gallons you have and what, like half, if I have 10 gallons and then like I'm at half a tank, well, I only have 5 gallons of gas left, and that lets you make your performance calculation, how far you can go and all that good stuff. Now, as time progressed, things got a little bit more sophisticated, and remote sensing became kind of the way to do things. And what that consisted of is like putting a float on the end of a rod with a series of linkages that connected to a arm that then connected to another spindle that had a needle on the end of it. And so as the float went up or down, that the series of linkages moved the needle from full to E, and then all the little gradations along the way. Now, the same thing could also be done by using a magnet, and you can have a little bit even more sophistication to your FQIS system that's there. Now, these are still, you'll still see these floating around out there. Largely, they've kind of gone away, but they are still available in some of the older, more antique aircraft. Now, it didn't take very much to make the jump between a linked float fuel quantity system to a totally remote fuel quantity system. The challenge with the linked one is that like the fuel cell still had to be very close to the pilot. So as airplanes got more and more sophisticated and got bigger, and the fuel got moved like out into the wings and further away from the pilot, the linkages became quite a challenge. So this system was contrived to where essentially the resistance that the float provided a pointer would be converted into a fuel indicating fuel quantity indicating system in the cockpit. It would, basically the less resistance that the tank resistor actually provided, the fuller the tank actually was. Whereas the more the resistance the tank actually provided, the closer to E it was, the more empty it was. And this is kind of like the basis of all of your GA fuel quantity systems even today. Now, modern fuel quantity systems use the same sort of idea, but the display is changed fairly dramatically. Instead of a little board-on tube or a pointer of some variety, now that you have digital displays on the left there, like you'll see those in like little RVs, experimental aircraft, and all the way to the right, that's kind of what your Garmin G1000 is gonna look like. But essentially, it's all using the same sort of thing. They're going to take and measure the current that's going through the system, and then as the float moves, it'll change the resistance in the tank itself. And then what happens is that the computer just determines like, hey, look, these electrical readings equate to so many gallons or whatever, and that's really all there is to most modern fuel quantity indicating systems. Now, heavy commercial aircraft use a capacitance system. They don't use the same type of system that like GA does. Now, so what is a capacitance type fuel system? Well, let's think about what a capacitor is. So here's the definition. It's a device that stores electricity. The amount it can store depends on three factors: the area of the plates, the distance between the plates, and the dielectric constant of the material separating the plates. Meaning that like these fuel probes that look like this that are installed in the wings of say like a 737, the distance between them won't change, the material won't change, but what will change and will change frequently is the dielectric, i.e. the fuel. So as the fuel changes in quantity, the system can store less and less electricity. That then gets sent to the fuel totalizer. It basically averages out all of the readings from these different fuel probes, and then it arrives at, hey, look, you've got like so much fuel on board in these different locations, and then gives a readout up to the pilot. Now, the advantage of this system is that there is no moving parts. So the other ones have floats or something akin to floats to actually give it some sort of reading. The fuel probe system, the capacitance fuel system, doesn't have any of that.
All right, now let's talk about fuel flow. The process of taking the fuel from its house up in the wing or in the bladder or wherever it's at, and routing it to the engine, and how we go about measuring the process of going from point A to point B and why that's important.
Okay, so first off, let's just try to understand why we want to know fuel flow anyways. It's pretty simple. Like we're trying to figure out the answer to an equation. We know that, say, we have 100 gallons. If we know that we burn 10 gallons per hour, then we know that, hey, look, we only have 10 hours to fly. Fuel flow effectively confirms that 10 gallons per hour rate, or allows us to manipulate it. If we know that the aircraft is supposed to burn 10 gallons per hour as a standard rate of fuel consumption, and then we can start to do things, let's say like leaning it out, or maybe like reducing our throttle setting, or any number of things to reduce that fuel consumption and still get the same flight time and ground speed and all that other good stuff across the across the flight, then that's good. And fuel flow basically allows us to track and monitor that simultaneously. If we are way higher than what we were supposed to be, then we know that we can't fly as far or as long as we had thought, because we're going to run out of fuel, for one. But it also lets us know that we have probably some sort of fuel leak, or something is not right to have a higher than normal fuel flow. Now, the graphic that you're looking at right now is just an example of a way that you can monitor fuel flow. So you have like fuel that's coming in, and then it's going out to the different injectors on the cylinders, and then you have this one nozzle that's off to the side that goes to a fuel pressure gauge. Now, it's a pressure gauge that'll let you know that, hey, look, this is the amount of pressure that is being put onto the fuel nozzles. But then you just recalibrate it, say like, hey, look, this is fuel flow. If we know that like 10 psi will result in like a gallon per hour of fuel flow, well then we just calibrate our gauge to reflect as such. But that's essentially like all fuel flow really is. And it's more common in higher end aircraft. Like you won't have you'll have fuel pressure gauges on let's say like my Cherokee 140 has a fuel pressure gauge, but it won't necessarily have a fuel flow gauge. Now you're kind of splitting hairs on what the difference is between the two, because effectively they're measuring the same thing, but know know that there is a slight. Okay, so this is a classic vane type fuel flow meter. The greater flow volume increases the deflection of the vane against a calibrated spring, and an auto send transmitter replicates the vane shaft rotation on the flight deck indicator, and it's calibrated in gallons or pounds of fuel per hour. So essentially, all that happens is that fuel will flow into that measuring vane, spin it around, and then the rate of spin will determine the what's indicated on the cockpit for the pilot to say like, hey, look, the fuel flow is a gallon an hour, a pound an hour, 10 gallons an hour, 10 pounds an hour, or what have you. And this is probably like the most common and probably like one of the most simple and older fuel flow gauge approaches that you're going to see out there. Okay, so a turbine engine aircraft will experience a really big range of fuel density from the temperature variations and fuel composition and all that good stuff. So an elaborate fuel flow device is used on those types of airplanes to help try to like cut through the noise. It measures fuel mass for accurate flow indication in the flight deck, and the mass flow indicator takes advantage of the direct relationship between fuel mass and viscosity. Fuel is swirled by a cylinder impeller that rotates at a fixed speed. The outflow deflects a turbine just downstream of that impeller. Now, the turbine is held with calibrated springs, and since the impeller motor swirls the fuel at a fixed rate, any variation of the turbine deflection is caused by the volume and viscosity of the fuel, and that viscosity component represents the mass of the fuel. So this mass fuel flow indicating system that we got here that gets used on, like say, your 737s, big turbine engine aircraft, they just all they're doing is measuring the direct relation between the viscosity and the mass to display the fuel flow in pounds per hour. That's basically saying like, hey, look, we know that the fuel is going to get colder the higher up we go. And so that's going to have a different relationship. But if we calibrate it with this mass fuel flow sensor, then we can still know how much fuel is going through there. Whereas if it was one of the other systems, the fuel flow indication would be off, and you would be making choice or decisions with your performance settings based on faulty information, which we don't want.
All right. In a rare case, you could have a situation where you need to get fuel off the airplane. You need to get it off quickly. So let's talk about fuel jettison and fuel dump systems, where you may find them, and what are some of the maintenance concerns you might have with them.
All right, so aircraft can generally take off with more weight than they can land with. Now, so you could have a situation where, let's say you take off and you've got enough fuel to cross, say, the Pacific Ocean. But all of a sudden, there's something that happens that makes you have to turn around. And so, whenever you turn back around, you realize, oh, well, like we can't land even though we're right over the airport because we have so much weight in the wings that the plane just simply won't stop in time. We'll run off at the end of the runway. And so in order to get down to a safe landing weight, something has to happen. So back in the day, you would just fly around in circles until you burn off enough fuel to land. Well, that has a couple of problems. One, it takes for a long time. And so if you have like some sort of emergent situation that you need to get on the ground fast, well, that's just not going to that just won't do. You're going to have to do something a little bit different. So this is where fuel jettison comes in. In order to get the plane down to an acceptable landing weight, simply a boost pump is turned on that goes to the fuel manifold, and then from the fuel manifold, a valve opens up that goes to wing or fuel dump ports on the tip of each wingtip, and allows the fuel to just basically get sprayed out into the air, where it basically evaporates and atomizes because it's getting pulled along at several hundred miles an hour and then opened up and sprayed out in the atmosphere. though that situation allows the plane to get down to a safe landing weight where the valve is closed and then it comes in and lands. What you're looking at here is British Airways 244, which had an issue with a passenger on board. Started reporting like there was like an odor in the cabin, and so they ended up having to divert. And whenever they diverted, they realized that they couldn't land where they were going to divert to, and so they had to dump fuel to land. Now, a few years ago, there was an issue where one of these 777s that was about to take off from or about to had taken off from San Francisco had a mechanical issue and had to come back. Well, as it came back into San Francisco, it started to dump its fuel. But what they forgot about was that they were over San Francisco. So you had a lot of people on the ground that were videotaping this plane, basically spray them with fuel, and it made it to be a big deal. So it's just a little fun story about fuel jettison and fuel dumping. But that's the general idea and the reason why that's there. It's just to simply get the plane down to a safe landing weight, so that way it could it can land and be safe. Whereas if it didn't, it would land heavy. You could have all kinds of problems, to include runway incursions. The plane would go off the end of the runway.